Alright, today I will show you how to calculate angles of regular polygons. So let's start by looking at a few examples and let's try to discover our formulas. Okay. First here is a triangle. Let's go ahead and take a look at the number of sides. A triangle has 3 sides. Quadrilateral has 4. Pentagon has 5. Hexagon is 6-sided polygon. Heptagon is 7 sides. Octagon has 8. Nonagon means 9. Decagon is a 10-sided polygon. Eventually, your number of sides get too big, so you just start referring to it as an n-gon, meaning 11-gon, 12-gon, 68-gon, and so on. So at this point, you can zoom in a bit, n refers to the number of sides. Now let's take a look at the diagonal. A diagonal is a line segment that connects two non-adjacent vertices. So connect two non-adjacent, meaning they are not touching, they're not next to each other. Non-adjacent vertices. Here's what I mean by this. In a triangle, if I pick one corner, any corner, it doesn't matter where you start, and I want to draw a line to connect this one corner to all the other corners. A diagonal would be a line that ends up going inside that polygon. So a triangle has no diagonals. Next up, quadrilateral. Let's say I pick this corner. If I connect this vertex over there, and that's the only vertex I can connect to. If I go this way, it's not inside the polygon. My line's not inside the polygon. If I go this way, again, my line's not inside the polygon. So those are not diagonals. So quadrilateral has 1. Pentagon, again, pick a corner, any corner. I'll pick this corner and then connect it to all the other corners. There's that. And then again, going from this corner to this corner is outside, this corner to this corner is outside. So you only go inside. So that's 2. I will go ahead and draw all the diagonals for the other shapes. Hexagon, if I pick this side, you can go here, there, there. Heptagon, I can't see the picture, so I'll just move on to octagon. Over here, over there, there, there. And the last one is thereabouts. Alright. So your heptagon has 1, 2, 3 diagonals. Hexagon. Notice a pattern 0, 1, 2, 3. That means heptagon has 4, octagon has 5, nonagon has 6, decagon has 7. Now let's look for a rule here. To go from this column, number of sides, to this column, number of diagonals, notice it's always behind by 3. 3 minus 3 is 0, 4 minus 3 is 1, 5 minus 3 is 2, 6 minus 3, 7 minus 3, 8 minus 3. So our relationship here is n, however many sides you have, minus 3. Next, let's look at the number of triangles. Number of triangles that we make after we draw that diagonal. Over here, there are no diagonals, and we see there's that one triangle. Quadrilateral, I can split that into 2 triangles. A pentagon is split into 1, 2, 3 triangles. Hexagon has 1, 2, 3, 4. Again, notice a pattern, 1, 2, 3, 4. Heptagon has 5, octagon has 6, nonagon has 7, and decagon has 8. Now I'm going to cover this row, and I want to focus on going from number of sides to number of triangles we make. What's that relationship? 3 minus 2 is 1, 4 minus 2, 5 minus 2, 6 minus 2, 7 minus 2, and so on. So my number of angles, or number of triangles, is however many sides you have, minus 2. This is important for looking at the interior angle sum of a polygon. So leading up to this, we've talked about how the three angles of a triangle add up to 180. So a triangle, the sum of the three angles is 180. For a quadrilateral, we have two triangles. So that's 2 times the 180. We get 360. For a pentagon, we have 3 triangles. So 3 triangles times 180. Get 540. And we'll move on from here. 4 times 180, get 720. 5 times 180, get me 900. And you get 1080. 1260. 1440. What we did is the number of triangles times 180. So let's write that there. 180 times number of triangles. So over here we have 180 times, we express number of triangles as n minus 2. So there's your equation. That's one version of the equation. Another version, algebraically, I can simplify this. Algebraically, it simplifies to 180n minus 360. So these two are equivalent. Right, measure of one interior angle. The three angles of a triangle, notice this as regular. Regular means all angles are congruent. So regular means all angles are congruent. So 180 divided by the three angles the triangle has is 60. 360 divided by the four angles of a quadrilateral. 540 divided by the five angles of a pentagon. 720 divided by the 6 angles of a hexagon. 900 divided by the 7 angles of a heptagon. And continuing on from here, 1080 divided by 8. 1260 divided by 9. And 1440 divided by 10. So what we did is the sum of the interior angles divided by the number of angles, which is also the number of sides. So I'll use this equation right here. The sum, which is this equation, 180 n minus 360 divided by the number of angles we have. And again, I can simplify this algebraically. This is equivalent to 180 minus 360 over n. So these two equations are the same. Now let's take a look at the measure of exterior angle. But before I do that, let's go to the sum of the exterior angles. So to do that, let me demonstrate off here to the side. I have here a hexagon. In my hexagon, the exterior angles are these lines right here. So first, let me trace out my hexagon. Okay. The exterior angles are the angles that extend on the outside. That's exterior. That's exterior. Over there. Over here. Over here, and over here. So those are my exterior angles. Now I want to make a demonstration here. Let's say I'm walking around this shape. If I start over here and I walk around, go all the way around this way, when I come back, I make a full circle. Full circle, turning all the way around, is 360 degrees. That means my exterior angle for any shape is 360 degrees. Okay. So now let's find the measure of one exterior angle. Going back to my hexagon, all the way around is 360, and I have 1, 2, 3, 4, 5, 6 exterior angles. So what we can do is 360 divided by the 6 angles, get me 60 degrees. That means each exterior angle is 60 degrees. So hexagon 60. So let's do that for the rest. Triangle, I have 360 to divide between the 3. That's 120. For quadrilateral, I have 4 over here. So 360 divided by 4 is 90. For pentagon, I have 5. 360 divided by 5 is 72. Heptagon, 360 divided by 7 is 51.43. Then I have 145, 140, and 36. So what we did is we have 360 degrees, which is all the way around outside, divided by your number of sides. Alright, so quick recap of what I went over. The important part for this unit, for this part, this section, is identifying what are the interior and exterior angles of regular polygons. We denote that by n. N is the number of sides. To go from number of sides to diagonals, you have 3 less diagonals, so n minus 3. to go from, let me zoom out so I can find that, to go from number of sides to number of triangles, n minus 2. To find the sum of those angles, it's the number of triangles times 180. So 180 times number of triangles, 180 times n minus 2, which algebraically is the same as this. To find the interior angle, it's the sum of the angles over here divided by the number of angles. So we have sum of angles on top divided by n, number of angles, which mathematically is the same here. And then for exterior angles, if I'm just walking on the outside and I go all the way around outside, that's a full circle, 360 degrees. So it's 360 degrees divided by the number of angles we have. And there you have calculating angles of regular polygons.